Bon, donc on va pouvoir passer à la partie séminaire de cette séance. Et c'est un très grand plaisir aujourd'hui d'accueillir, je dirais, d'accueillir à nouveau Corinna Kollath à Paris. Puisque Corinna a été à l'école polytechnique pendant quelques années, dans les années 2000, j'ai oublié, 10, quelque chose comme ça. Corinna est une théoricienne de la physique des atomes froids et de la physique des systèmes quantiques à forte corrélation. Elle a fait une très belle thèse sous la direction d'Uli Schölweck, dans laquelle elle a considérablement développé les méthodes de DMRG pour le transport et la physique de non-équilibre en temps réel. Et elle a ensuite fait un postdoc avec Thierry Jamarchi à l'Université de Genève, puis est venue en France pendant quelques années, et c'est un très très bon souvenir d'avoir beaucoup collaboré avec elle, et des postdocs et des étudiants, en particulier sur ces méthodes de refroidissement dont j'ai plusieurs fois parlé dans ce cours et qui sont maintenant implémentées dans les expériences, et puis toutes sortes d'autres choses qu'on a faites ensemble. Elle est ensuite partie à l'Université de Genève comme professeure associée, et depuis plusieurs années maintenant, elle est professeure à l'Université de Bonn, en Allemagne, où elle continue ses travaux, en particulier au cours des années récentes, sur la théorie des atomes froids dans les cavités optiques. Et donc, c'est ce dont elle va nous parler aujourd'hui, et je pense que le séminaire sera aussi un bon complément du séminaire de Jean-Christophe Bantu, qui nous a parlé des aspects expérimentaux. Voilà, merci Corinna, un très grand plaisir.
Yes, so thanks very much. It's always a great pleasure to be back here in Paris. I mean, it was a fantastic time during my career to work here with many groups in this very exciting field of cold atoms and strongly correlated systems, like Antoine said. So today I would like to endeavor a little bit into putting now these cold atomic gases, which Antoine was telling a lot about, into optical cavities, and telling you about some theoretical advancements we did in the last years in these systems. Before I start, I would like to thank my collaborators, because I always forget it in the end, and I mean they have a major contribution to all this work, so let me thank them now. So in particular, it's Katalin Halati, who was a PhD in my group and is continuing to work with me now, a postdoc in the group of Thierry Jamarchi, Simon Jäger, who has just started a postdoc in my group, but we collaborated already before a little bit on these cavity issues, so he has a very major contribution as well, and Luisa Tolle, a PhD, who did now a lot of work on these fermionic gases in the optical cavities. And let me as well acknowledge the work with Aminé Khan, Thierry Jamarchi, Helmut Rietsch, Giovanna Morici, Ala Bechevenkov, and Achim Roche. And as I told you, I will now take these cold gases, which Antoine was giving these beautiful lectures about and has shown you that there is a lot of fascinating physics in these systems, and I will try to combine them with another ingredients, which are these cavities. Cavities you know here in particular because of Serge Haroche, who has pioneered a lot of work in these systems. He has used mainly the microwave cavities. And so what are these cavities? You have two kind of mirrors for electromagnetic radiation, and you confine your electromagnetic radiation within this confinement. And this is, if it's confined for a long time, these are these cavities where you can really see that the light is then behaving like a quantum harmonic oscillator. So here you have the light mode A, which creates a photon in the light field, and so you have just a harmonic oscillator in these systems, which describes the physics of the light. So one can say you are now combining here the quantum photons, or really the quantum nature of the photons, with these cold atomic gases, where Antoine has shown you the beautiful quantum physics which is arising in these systems. There are many different cavities. I mean, here these microwave cavities had been used a lot. There's a big field of circuit QED where you use superconducting cavities. There's terahertz cavities, there are plasmonic cavities. So I mean, it's really a big, big field. And what I will focus on are optical cavities here, which here I took a nice picture of a fiber cavity. But I mean, we will use the normal high finesse optical cavities in this talk, or like they are used in the groups of Timon Esslinger at the ETH, Andreas Hemmerich in Hamburg, or Jean-Philippe Brontu, who gave a seminar just very recently here at the ENS. So why is it nice to have now matter in these cavities? Because you can have a very strong coupling between the light in the cavities and the matter. And I mean, there had been many proposals how to use this for quantum sensing, quantum information processing, quantum connectivity, or as well to just realize these novel quantum states. And what I would like to do is really to put a many-body quantum gas in these optical cavities and show you what kind of fascinating fundamental effects arise by the fluctuations of the cavity atom coupling in these systems. How does this cavity couple to our cold atoms? So we have the mirrors of these optical cavities. We don't pump the cavity from the mirror side, but we pump it transversely, which makes that we don't have a light field in the cavity just by the pump. So we don't classically pump the cavity field, but we just wait that this comes about by the interaction with the atoms. And how this is possible is we take this transverse pump beam, a photon can arrive to an atom, it can excite this atom virtually to an excited state, and via the cavity it can decay back into the same internal state of the atom, but a different momentum state in the system. And so this is this process which I have sketched here. So you virtually excite your atom, but you then de-excite it again by scattering into the cavity. But you can certainly have as well the other way the process. You can scatter if there is a cavity photon already present. You can as well use this to scatter something into your laser pump. So this gives you, if you want to describe it in a simplified picture, so we do a rotating wave approximation, we eliminate the excited state and do some other approximations, we can arrive to a Hamiltonian description here, which is just the coupling of really here our cavity modes. So the A and A dagger are for the single mode in the cavity, which I'm considering here. We have our pump beam, which is omega here in this case, so gives a prefactor to this cavity coupling, and we couple to an operator of the atoms. So here I call this delta, but this operator of the atoms can be very different depending on the coupling scheme, how you set up the geometry, the structure between the laser coupling and the atoms. So you have a lot of possibility to tune this here. There is one particularity, these cavities are never perfect. So this cavity always leak out some of the light field, and so you have losses of the photons, and by these are open systems. So typically it's not good to describe them really as closed systems, but you need to take this leaking of the cavity field into account. And this is why these are really nice realizations of the systems which have had a lot of interest in the last years, which is having a quantum many-body system which is coupled to a kind of tailored environment. So now our environment is the cavity photon plus the loss process in this system. And by the coupling, which we can engineer in several ways, we can tailor what we are coupling to in our system. What is the advantage, or why has this been of interest in the last decade a lot? Because in these systems what we have is we need to describe this by a master equation, and by this we have not a normal thermal state in these systems, but we have steady states which are reached in this system. And this is called this attractor dynamics, where we flow against the steady state. And if we perturb the system just for a short time, it will always flow back to this steady state and is by this very robust against some perturbations which we can imagine in the system. And so this is as well something we will take into account by describing the system really, this open nature of the system in our theoretical approaches. I'm sure Jean-Philippe Prontu has given you already a very nice introduction and as well about, talk about the self-organization transition which can happen in these systems. But let me repeat it just here as well in a relatively small fashion. So we are now taking here our optical cavity, we have our atom cloud in it, and we transversely pump this system. What is happening then is that first of all we have only fluctuations of this photon field, and there is not really an average value of the photon field arising. Only if we pump hard enough and enough photons scatter into the cavity, we see that there is a transition at some critical value here. So this is the pump beam amplitude, and we have a transition that the cavity is then occupied spontaneously. And so we have as well a standing light field here by this cavity occupation, and the atoms are ordering now in a checkerboard pattern because of the interaction with this light field. And so this is a phase transition which was known by the Dicke model and had been realized kind of approximately in this cold atomic gas setup. And I find this very fascinating that you really just pump from the transverse side and you have this spontaneous formation of the field. So there is a Z2 symmetry here depending on the amplitude of the field. So which checkerboard you are kind of realization you are taking in the experiment, and you are breaking this spontaneously. So this had been seen very nicely at the ETH in Tillmans Esslinger's group, but as well in Andreas Hemmerich's group in Hamburg almost at the same time. Since then, a lot has been done in these systems. I mean, there had been very nice work on the bosonic gases. There had been a lot of different directions, realizations. I mean, two cavities where they could see a spontaneous formation of the lattice and kind of super solid in this way. And there had been this nice work by Jean-Philippe Prontu, where you see as well this self-organization for fermionic cloud in these systems. And I think he gave a whole seminar on this, and so you might know the details very well, which I'm not repeating here in detail. But what is happening here is the same as I have shown you for the bosonic gas. So you have a sudden occupation of the cavity mode, and by this you get a density ordering, so density wave ordering in your fermionic gas. On the theoretical side, there had been a lot of very nice description. I mean, there are very nice reviews on this. There's one by Helmut Rich and collaborators, and now a newer one here by Meve Kha, who have really put together very nice reviews. And there is a whole plethora of work looking at spin classes, superconducting phases, Payal's transition, super solid transition. So a lot of different things are proposed to be realized here in this self-organization transition. Since I'm very much biased, I just want to mention our work where we have proposed to as well use this kind of cavity pump to realize dynamical spin-orbit coupling or dynamical artificial gate fields in this system to get topologically non-trivial phases. But I don't want to describe this in detail. What I would like to show you today is how these fluctuations of the cavity field coupling can become important both for the steady state and as well for the dynamics in these systems. And this is what I would like to describe you in the following. And so the first thing is that I would like to describe you what influence do have these fluctuations on this phase transition, on the steady state phase transition here, And I will show you that we have seen a new type of bistability, which is induced by these fluctuations. And then I hope I will have time as well to tell you a little bit about the spreading of correlations in these systems by the coupling to the cavity, because this is now a global coupling to this cavity, and this has a very different kind of spreading. One expects a supersonic spreading of your excitations in contrast to light cone-like behaviors, as you would see it normally in these systems if they are not coupled to cavities. And I don't think I will get to the last point, but just to give you a teaser, one can have as well approximate self-organized symmetries in these systems, which are kind of arising by the occupation of the cavity field. So let me start by introducing the model we are using, because we do quite a few approximations to arrive there. I will not detail this. Maybe Jean-Philippe Prontu has detailed a little bit how to get to these kind of situations. But what I'm considering here is these optical cavities represented here by these mirrors. And then I will assume already a lattice being present in this system, so an external optical lattice, which I haven't drawn here, which are confining the atoms additional to the cavity field and to the pump field. Then we will have the pump beam, and so the atoms are described by a normal Hubbard model or Bose-Hubbard model in our situation, and then we take the coupling of the cavity on top of this. So here I have this Hubbard model now written down for fermions. We have the description of the cavity photon as the harmonic oscillator. We have the coupling of our cavity photon here linearly to the operator of the atoms. And here what we are using is that the commensurability between the lattice, which is formed by this cavity photon, and the optical lattice is a period of 2, which means that one has the coupling to an even odd kind of density in this system. So every second side is coupled in a different way to this lattice. So this is the setup which is used, for example, for the bosons in Tillmann-Esslinger's group, and this is why we first took this one. But what is important as well is that we take here not just the Hamiltonian evolution into account, but we really go to the Lindblad master equation, where we take the cavity losses into account here just by this loss or dissipator term here, like it is quite often done in these quantum optics systems. Theoretically, this model is quite challenging. I mean, Antoine described you how already just describing the atoms themselves is challenging. And now we have on top of this large photonic Hilbert space, which we couple to. We have the global coupling between the light and the matter, and we have the dissipative nature, which we have to overcome in our descriptions. So they are very nice work based on a simplification, which gives already a big insight into what one is doing, which is just to do a mean field decoupling of the atoms and the cavities, and then adiabatically eliminate the cavity, because the cavity field is very quickly evolving, and to then see what this is doing for the atoms. So what one gets by this is an effective Hamiltonian for the atoms, typically a ionic Hubbard model or Bose-Hubbard model or something similar. And then what one has is that people typically consider only the ground state of this one to see what is happening. But in this theory, all the eigenstates are steady states of the system. So it's a very arbitrary choice to take just the ground state as the steady state value. And so we wanted to go or to get around this arbitrariness and to take fluctuations into account, which really settle then what steady state you are going into. But let me give you first the mean field results so that we can then compare to them later in the talk. So this is a typical phase diagram, which I will show you in one or the other way several times. So this here is the photon number in the cavity field, and this is the pump power here. So it's the strength of the coupling between the photon and the atoms. And you have here a phase transition which you see between an empty cavity and an occupied cavity. Here, by rising the photon number, you see that the cavity becomes occupied. At the same time, you have a density wave here sketched in one dimension, which is developing. So you will have that the cavity lifts the degeneracy between these two lattice wells, and one lattice well is preferred, and you have this checkerboard pattern of your density in the atoms. So here you have a pure state for the atomic, and it's a charge density wave. And we were wondering how to get, or what is really happening in the system if we take fluctuations into account. And so what is happening there, let me just give you a sketch so that you remember this, is our mean field state here is not really the steady state. So we are not balanced here, but we need really the fluctuations to see what is the steady state we are flowing to. And we see that this is changing both the steady state and the dynamics quite a bit. We are not the only one who did this, take these fluctuations into account. Giuliano also here did a very nice work on it. And I mean, there are many earlier works by Giovanna Morigi and Helmut Rich and all others. But I think in our way to take this into account, it becomes very clear what these fluctuations do to the system. And so what we are doing is to take our mean field model, and then we do a perturbation around this. So what we are taking is here the mean field model, and then we take the fluctuations around this in the coupling as the perturbation. And so we calculate the dissipation-free subspace of the mean field model and take then photon fluctuations which are coupling to a virtual excitation, like you know it from the exchange coupling in the Hubbard model. But now here we need to do it for this Lindblad master equation to do this virtual coupling in the system. And so this was a work with Alla Becherbenko and Achim Roche together to set this perturbation up around this mean field coupling. Typically, the equations we get out of this are still very complicated, and what we do to analyze them further is to do an approximation that we say, okay, one approximation is that we take a thermal state in the atomic sector. And so if you do this, it reduces to a very simple expression. We do have that the evolution of our fermionic or bosonic atomic Hamiltonian is just given by a susceptibility of the operator which we are coupling to in the system, and this integral around it. And so this is what I will first show you, what we get out of this method if we do take this thermal ansatz and we try to see what is happening at the transition. And so here now I show you this for this fermionic Hubbard model, what is happening. Again, we have here the scaled photon number. We have here our coupling to the pump or the pump laser strength, so the atom cavity coupling. And we do see here this black one is just the mean field expression where we had seen this phase transition between the empty cavity and the filled cavity over here. And we do see now in our curve, which we get, we see something very similar. The critical value is shifted, so the fluctuations do shift it to higher coupling strengths. We need a higher pumping to really get the ordering. But what is surprising is that, first of all, it rises, but then it plateaus here for a certain period. And this is that the fluctuations really suppress kind of the photon occupation, because what they are doing is to heat up the system more and more by having more and more scattering with the photons which are dissipatively in this system. So we get here a finite temperature which is encoded in this color coding. We are going here up in temperature, and you see we are heating more and more our system up. So we don't have a t equals 0 transition here. Already here we have a finite mixed state. So we really need to describe this away of the pure state and need to take these effects into account here. to show you as well a little bit what the atoms are doing, I repeat this phase diagram now here. So this is exactly what I have shown you before. This is now looking at the imbalance between even and odd sides for the fermionic atoms to see how this fermionic state is really forming the checkerboard pattern. And you see that the checkerboard pattern is formed here. You jump to almost to 0.8 of this imbalance in this system. But then the temperature does strongly destroy this again, and you have a lot of fluctuations in the system. So the checkerboard pattern is not as good as you would imagine it in the zero temperature transition, which is going up here in this system. And so here I plot as well this effective temperature. Again, you see we start already from a finite value. So even below the critical pump, we have that the fluctuations is heating up our system already considerably, sadly, because this is a few, of the order of the hopping. And then we go further up in the temperature and heat it up to really a high temperature. But let me tell you that it's not as bad, because here around this where we have this minimal temperature, there is really, if one zooms in, one sees here a minimum, and this is a cooling by the cavity. So it's an effect where we are close to the resonance, where we have this cavity offset, which is generated. This excitation here is close to the energy the cavity photon can carry away. And by this, we get a big carrying away of this energy by the cavity photon, and we get a cavity cooling, which it's typically called. So if we come from very high temperatures, the cavity can help us to cool down to these low temperatures, but to get lower is a little bit difficult in this situation. Okay, that was, we found that we have really to take this into account, but then we went to higher interaction strength, and we had a look what is happening there. And then what we saw is that something which we didn't expect was happening. So we were looking for a plateau value here of our photon density, or of this density imbalance of the checkerboard pattern. But what we found in contrast is a bistable solution. So we have here a stable solution, and we have here a second stable solution which sets in. This is only at high interaction strength, and it's not there if we set the double occupancy to 0. So then we always stay in this lower branch. Comparing to the mean field solution without the fluctuations, we see as well that this bistability is not there if we don't take the fluctuations into account. So it's really generated by the fluctuations, the interplay of the fluctuations and the interaction in the system of our cavity atom coupling. So let us look a little bit more at this second solution now. And so this was the solution I showed you before, and this is as well the solution if we neglect the double occupancies. But if we allow for the double occupancies, we get this other solution coming up. So here I show you directly the density imbalance versus the coupling strength. This was the first solution which was damped out, or damped going down by the heating of the system. But we see that we have a much higher imbalance and almost an imperfect, a perfect imbalance here in this second solution, which sets in. And so you see as well in the temperature, it's really much cooler than the heated temperature of this first solution in the system. And we could identify that this is due again to this cavity cooling, but now between different excitations. And so this is now between the excitation where we have a double occupancy on the lower side or occupying both sides with a single particle. So we have here the energy difference, which is this energy difference between the valves. And if we are close to that, the cavity photon can bring or take an energy which can make this kind of excitation, we get this much lower temperature. So we have a cavity cooling, which is now really using a many-body resonance here to do the cooling in the system to a lower temperature. But you see in my picture, I haven't really taken care of the spins. So the cavity cooling we can get here is to a lower temperature, which is dominated by the charge gap, or below the charge gap. But we have to inquire what is about the spin later on. Okay, this we liked much more. So we have now as well not only this enormous heating if we switch on the pump power of our cavity. So now the pump power is this y-axis here, and we have the interaction strength, because we saw that the interaction strength is very important. And you see these are values where the interaction over the hopping, so sorry to confuse you here, the J is the hopping, which we use, is of the order of 20, so it's huge. So it's really for the strongly interacting regime that we do see this bistability. Otherwise, it becomes much more narrower, and we cannot resolve it in a very good fashion. This is relatively recent work. As I said, Luisa Tolle was the leading PhD on this work. And I mean, there are now many open questions. What kind of bistability, or what does this bistability have for an influence on the dynamics of the system? How is it if we go even beyond this perturbation theory? Does it survive? Do we see signatures of it? And what is it, causing here, or what kind of new dynamics would it be about? And so with this, I hope I have shown you that these fluctuations are really important to take them into account. In particular, if one wants to propose very nice phases which are living at low temperatures, one has to make sure that they survive and one can really reach them. But I mean, we have as well a way to kind of cool into some of these situations by using resonances between the cavity and the internal many-body energy levels of the atoms. One thing which these cavities are always said to be good for is as well to give you a global interaction between the atoms. So it's said that they give you an effectively long-range interaction. So let's have a look. What is one of the biggest consequences of this long-range interaction is that the spreading of correlations in the system will be changed totally. And this is something I would like to show you now in the following. And this is work with Katalin Halati and Simon Jäger together and Amine Shaikan. Why is it important to look at this spreading? I mean, in the last decades, the experiments were advancing more and more to really time-dependently as well in the solids, to have the femtosecond laser pumps to really dynamically steer and control these systems. And we need to know what are the timescales for evolving these correlations. And if we take just a relativistic theory, we know the maximum speed we can get is the speed of light. But in these quantum systems, it's not that clear what kind of bound is built in. And so there had been a very nice work by Leap and Robinson, who looked at short-range spin systems and predicted that correlations could maximally spread with a velocity, with a certain velocity, so that one gets an evolution. Here is the time and the distance, and the correlation can only form within this light cone here. So we need a certain time to reach a certain distance in these systems. So this is called light cone-like spreading, and is valid, this picture, at short-range couplings. I couldn't resist to put as well the nice collaboration with Emanuel's Bloch group, which is now many years ago, where one saw this light cone-like spreading in a Bose-Hubbard model by doing a quench in the interaction. And one saw in the density-density correlations here, we saw this kind of light cone-like spreading and compared it with our theoretical work to identify it. But now, what is now happening with this global range coupling? So there is a lot of things which had been explored in the last decades on algebraically coupled systems, and there are many fascinating phenomena. And the global range coupling is always said to be boring, because one expects that there is an instantaneous coupling possible, or a change of the correlations possible in time and distance at all positions. And we were now curious how this now is really in real systems where we have this interplay between the short-range couplings and this global range coupling of the cavity mediated by the cavity. So we kind of have both this situation, but we have as well this dominating global range couplings which we switch on by the cavity coupling. And so what we are looking at is the density-density correlation, which we will be monitoring, because this is the case, because if we don't have the kinetic energy, this correlation would just be a constant of motion and would not evolve at all. And so we are really seeing here then the effect of how the kinetic term, the short-range coupling, interacts with the global coupling the best. What we are doing is to prepare just a checkerboard pattern. So we do a 1, 0, 1, 0 of the atoms. And here we are changing, before what I told you was for any dimensional system, but here now we are confining ourselves on a one-dimensional system, because there we can use a numerical method, which is called the matrix product state method. Antoine mentioned it beforehand. And now this is developed, a development which Katalin Halati has implemented, where we take the cavity explicitly into account and we couple it to the atomic side, and we can, by this, really look at the evolution of this. What is crucial here is that we have an adaptation, a dynamical adaptation of the local dimension of this cavity side, otherwise it's blowing into our face very early on. Additionally, we compare as well to a truncated Wigner approximation, which we will see later on in our simulations. And let me now show you here 3 different situations. So what I changed here is the atom cavity coupling from a small amount to a large amount over here. So what we do have is now again this plot where we have the time here and the distance here, and we see how correlations are spreading in this system. Here, this is for a very low coupling, and we see it's almost light cone-like. We almost don't see something which is happening here, at least at short-range correlations. So we kind of see this light cone-like behavior. Certainly, if we go to very long times and long distances, as well here, the global interaction will set in and will destroy this light cone. And if we go over to this very high or a much higher coupling, we see that additional to this light cone which is setting in here, there's something happening almost at the same time for all these different distances of our correlations, which we call now this instantaneous evolution. And if one really does cuts here, one sees that it's algebraically growing and then reaching a maximum, which we see here, and then oscillating, such that we see this structure in this situation. So what I would like to show you, that we can see exactly this global range spreading, which is this instantaneous spreading here. But if you go to a low coupling, it's overwhelmed by the light cone-like evolution, and only at larger distances it can set in and take over the evolution. So in experiments, one would need to see where, in which regime are we, can we really use this global range coupling? We have to make it strong enough to see these instantaneous changes. We were now wondering, what is the origin of this, or how can we see this? And is it just a very boring behavior if you take a classical light field which we switch at all positions at the same time? So if we just go into this mean field Hamiltonian and we switch on this classical field, do we see something similar? And there we saw, so here I'm comparing the full calculation to this classical field, that then this instantaneous rise is really absent. So we cannot get this by just switching on a global field, which certainly changes the density at all positions at the same time, but not the correlations yet in these systems. So then we switched on the fluctuations in the classical field, which one can do by taking the truncated Wigner approximation, which is an approximation which takes a stochastic sampling of the cavity fields and the atoms into account. And here we see we see something which is already very similar to what we had over here. So we see this kind of a rising instantaneous change in these systems. And so there we can, as well in this truncated Wigner approximation, see that the stochastic fluctuations of the cavity field are really important to carry this long range or global range correlation and to initiate them in our system. As a last thing, what we did is just to probe that it's as well very robust, this effect. If we take now just this density, or this interaction, which is, if one neglects retardation effects, it's just a square coupling of the density, staggered density in our system, and we do recover as well the kind of same evolution. So it's not necessarily that it's really this cavity field which we have here, but it's really due to this effective long-range nature of the global interactions, which we see this spreading. But I mean, the cavity field is a nice, tunable environment where we can induce this very easily. And so this is what I would like, or I hope I have shown you in this part of the talk, that one really can see this instantaneous spreading. And this is certainly very exciting for a lot of different fields. I mean, people want to use this now for quantum processing, try to get entanglement or this correlation created very fast over long distances, and to see how this kind of correlation spreading can be done. Oops, sorry for this. Somehow it moved. So, and with this, I would just like to end by giving you as well a teaser on the last thing that one can get as well, symmetries which are spontaneously ordered or self-organized in this system. But there I don't want to go into the details because I don't think I have the time. I would like to leave at least a few minutes for questions. But just let me mention that, I mean, there had been these very, very nice experiments, one of the first ones of cold atoms and optical lattices, where the collapse and revival of wave functions had been seen. And it was seen that a coherence in the system can survive for quite long time. So you get here a coherent picture. If you hold for a certain time, you can recover the coherence after some time. Whereas in between, it looked like a total incoherent mixture of the atoms. And this was due to symmetries in the system, or that one has this very high U interaction strength. And one can get something self-organized now in the cavity by ramping up this cavity, or by ramping up the pump power. This kind of symmetries can as well evolve. And one can see something similar, that coherences can be there for very, very long times. And just as a teaser, so if you are interested, I am happy to discuss this with you later. And with this, I would like as well to finish. And I hope I have conveyed you that fluctuations are really important in these cavity atom systems. I mean, we can see already some of the features without taking them into account. But if we want to determine the nature of the phase transition, or if we want to determine the spreading of correlations, or things like this, we really need to take them into account and to work a bit harder as a theoretician to see what they are doing. At the other hand, they are as well bringing nice features like bistabilities, like cooling into the system. So I think it's worth the effort to go beyond the simple pictures and take them into account. And so I would like to thank you for your attention.